Creating exponential functions, Part 1. We will create growth and decay exponential functions mainly from verbal descriptions. The main strategy is to use the verbal descriptions to determine if the relation can be modeled by an exponential function. Then use 2 points and the exponential regression feature in the graphing calculator to determine the function. As in linear functions, there are key words and phrases that indicate an exponential relationship. First, there's a rate of growth or rate of decline. A percentage increase or percentage decrease would indicate an exponential function. Interest rate is an exponential function phrase. And finally, half-life would be an exponential decline function phrase. To create an exponential function, 2 things are needed. First, we need a starting point or amount. And this might be a starting amount of money, a starting population, a starting rate of production, or a starting amount of a substance. Typically, this will happen at time equals 0, or an input value of 0. Secondly, we need a rate of growth or decline. This can be given as a percentage increase or decrease, or can be written as increased by a factor of or decreased by a factor of. And we need to remember that factor means something that is multiplied. It can also be written doubled every year, for example, or is cut in 4 parts every week. Well, cut in 4 parts would be 0.25 times, so the factor would be 0.25. It helps to remember that a percentage reduction means the new percentage found by subtracting the reduction from 100%. And for example, a 30% reduction means that the factor of reduction would be 100 minus 30, or 70%, or it would be a factor of 0.7. For percentage increase, the percentage being increased is added to 100. For example, a 100% increase means that 100 is added to the base percentage of 100, so the new percentage is 200% of the original amount or number, so 200% is a factor of 2. Any factor greater than 1 or percentage greater than 100 is a rate of growth exponential function. Any factor less than 1 or percentage less than 100 is an exponential function with a rate of decline. Situation 1. John is investing $1,100 in an account that pays 4.75% interest annually. How much will the account value increase to after 4 years? So that's the first question. And the follow-up question, after how many years will the account value exceed $1,800? Well, here's our standard exponential function y equals a b to the power of x. And the a is the coefficient or starting point or amount. And then the b is the base, so the b will be the factor. In this problem, the starting point is called the principal in money, or 1,100. So we replace the a with 1,100. The base is found by taking 4.75% and adding it to 100% for a total of 104.75%. And the 104.75% is converted to a factor by dividing by 100 for a factor of 1.0475. The factor of 1.0475 replaces the base in the equation, and so now we have y equals 1,100 times 1.0475 to the power of x. And we can put the equation in our graphing calculator to evaluate. And here we place it, and if you'll notice, the power key, which is right below the clear key, you press that first, and then x goes after it. You're probably used to putting a 3 or a 2 or some other exponent to the right, but in exponential functions, the x goes to the far right, to the power of x. Now we go to our table view, and by pressing second graph, and we can go down to 4 years because it asks for 4 years, and we can see that after 4 years, the account value is going to be $1,324.40. And to get our account value, John's account value, to at least $1,800, we need to scroll down to 11 years, and we can see that 11 years the account value is in fact over $1,800. And therefore, the answers are $1,324.40 after 4 years and 11 years for the account value exceeding $1,800. Situation 2. Sandy is buying a car for $25,000. If its value depreciates at a 30% annual rate, what will be its value after 3 years? In this case, the starting point or coefficient is 25,000. The base will be 100% minus the 30% depreciation rate for a total of 70%. And 70% converted to a factor is 0.7. We divide that 70 by 100. And so this is our exponential function. Y equals 25,000 times 0.7 to the power of x. And we can place that in our y equals view in our graphing calculator. And from there we can go to our table view by pressing second graph. And we can go down to 3 years, and we see that after 3 years, we're going to have an account a car value of $8,575. And let's go to situation 3. If the population of the United States is 295 million at the start of 2009, what will the population be at the beginning of 2018 if it grows at an annual rate of 1.2%? Now stop the video and see if you can solve it. Remember that the starting point or coefficient is the starting population and the base has to do with the growth rate. In this case, the starting point is 295 million. The base will be 1.012. And the time to be evaluated for will be 9 years because it takes 9 years to get from 2009 to 2018. Go ahead and see if you can work it out. Okay, so we can put the equation in place instead of writing out the whole 295 million. For shorthand, I just put 295 times 1.012 to the power of x, and if we go down to press second graph and go down to 9 years, we have a population of a little above 328 million. So to summarize, first we find the starting point, and usually it's a value or amount. We need to secondly find the base by taking a percentage increase or decrease and turning it into a factor to multiply by the starting amount. Factors or bases greater than 1 are growth functions, and less than 1, they are decline functions. And finally, we need to create the exponential function by placing y equals the starting amount times the factor to the power of x. Thanks for viewing. I hope this lesson has been helpful.